let's take a look at more about nuclear physics and more about radioactive decay. First, let's think about evidence for the strong nuclear force. The primary evidence for it is the stability of a nucleus. If you think about a nucleus, it's protons and neutrons in a very small location, a very small volume. Without a strong nuclear force, the nucleus would not make any sense. Without the strong nuclear force, Coulomb repulsion would cause the nucleus to separate, or at least would cause the protons to separate. So some kind of nuclear force is implied by the stability of a nucleus, and that force is what we call the strong nuclear force. Another piece of evidence to indicate that the strong nuclear force exists is deviations from Rutherford scattering. So when we thought about that, remember, if you send in an alpha particle towards a nucleus, it will experience Rutherford scattering as long as it doesn't enter the nucleus. However, if the alpha does enter the nucleus, then we no longer get anything resembling Rutherford scattering, which means that some kind of new force is present between the nucleons in the alpha particle and the nucleons in the nucleus, and this new force is the strong force. Now let's look at stable nuclides in a new kind of graph. We're going to create a graph of number of neutrons in the nuclide versus number of protons in the nuclide. And before I show you where the stable nuclides are, I'm going to draw the 1-to-1 line, a line where we have an equal number of neutrons and protons. So it turns out that for very low Z, lower than about 15 or 20, small nuclei have approximately the same number of protons and neutrons. So stable nuclei exist about here. However, when we get to larger nuclei, nuclei with more than 20 nucleons in them, it varies. It deviates from this 1-to-1 line. As we have more protons, we have more of this longer range Coulomb force of repulsion. If we have more of this long range Coulomb repulsion within the nucleus, or between the protons within the nucleus, that requires more neutrons for stability. And that's because the strong nuclear force is a very short-range force. It really is only present between nearest neighbors within the nucleus. The Coulomb force is a longer-range force. So if we add a proton to a nucleus, that's going to add quite a bit to the amount of repulsion that's experienced. Every other proton will feel more repulsion. But because the strong force is a very short-range force, we need more neutrons to be added per additional proton as the proton number gets very large. Now let's go back to the binding energy per nucleon graph that we've seen before. Here's a rough sketch of it. And I want to point out something over here. Notice that on the left side of the graph, where we have fewer than about 60 nucleons, if the nucleus contains fewer nucleons, then adding a single nucleon should have more of an effect on the nucleus, which is why the curve is so steep. Over here on the right side of the graph, when we're greater than 60 nucleons, adding a single nucleon has relatively little effect on the binding energy per nucleon. So that's why the graph over here has such a gentle slope, whereas over on the left side, we have such a steep slope. And now we'll move on to nuclear energy levels. So it turns out that observations of alpha and gamma emission from nuclei suggest that nuclei have discrete energy levels, sort of like how electrons exist in discrete energy levels in the outer part of an atom. So I'll draw an example of how these are depicted. Let's say that we have some element X, and it decays by alpha and gamma emission into element Y. It turns out that this element Y may have multiple energy levels, nuclear energy levels. And I'm going to write down what those energy levels might be. And when the decay occurs, when the alpha and gamma occur, you can have different combinations of alpha and gamma. So for example, we could have a decay of an alpha and a gamma where we get the alpha emitting 100 keV and then the gamma emitting 60 keV to take us all the way down to the lowest energy state. Or we could have an alpha emitted with 130 keV and then get a gamma with 30 keV coming out. Or we could have an alpha descending 150 keV, taking out 150 keV of energy with it, and then a gamma emitting 10 keV. Or we could just get a single alpha going 160 keV. But the point is that we only observe certain energies of alphas and gammas emitted by a nuclide. And this is evidence for nuclear energy levels. Now notice that I left out beta. And the reason why I left out beta is because when you observe beta radiation, it is a little more complicated. So initially, when beta radiation was discovered, there was no knowledge of the neutrino or the antineutrino. When beta plus and beta minus radiation was observed, only the positron and the electron were observed. And it turns out that when scientists observed the positron and the electron that were emitted in beta plus and beta minus radiation, they did not have discrete energies. They had a continuous energy spectrum. And the graph that's usually associated with that looks like this. On the vertical axis, we're going to say the number of positrons or electrons with a certain energy, and on the horizontal axis, we're going to have the energy of the electron or positron that's emitted in the decay. It looks something like this. It's not discrete, it's continuous. And this is surprising because if there are discrete energy levels within the nucleus, the emitted particles in beta decay should also have discrete energies, but they don't. And the solution to this is that, sure, positrons and electrons don't have discrete energy levels, but it turns out that there is another particle that's emitted with the positron and the electron, which we now know as the electron neutrino and the electron antineutrino. And it turns out that the total energy of the positron and the electron neutrino, or the electron and the electron antineutrino, the sum of the energy of those two objects is discrete. So when we're looking at the continuous energy spectrum of the electron or the positron, we're not seeing the whole story. We are missing the other energy that's lost to the electron neutrino or the electron antineutrino. And now let's talk more about radioactive decay. So if you remember, the rate of decay of nuclei is proportional to the number of nuclei for radioactive decay. So we can write down this expression. Now, another way to write this would be that the negative of the rate of change in the number of nuclei is equal to some constant times the number of nuclei. And I'm going to write that constant as the letter lambda. A solution to this equation is that the number of nuclei is equal to the number of nuclei at the beginning times e to the minus lambda times t. And when we write it this way, that lambda right there, that constant, is called the decay constant. It has units of inverse seconds, and it's unique to each radioactive nuclide. And I want to emphasize this decay constant is not the same as the half-life. It can be related to the half-life, but it is not the same. And this n0, I said, is the number of nuclei at the beginning. It's the number of nuclei at whatever time we're calling 0. Now back to the decay constant. One way to interpret it is it's the probability per second that a nucleus will decay. Now, it's a little bit trickier than that, so I'm going to write down an expression. The decay constant is equal to the probability of decay per some amount of time. But that's only really true if the amount of time that we're talking about is much less than a half-life. Now if we go to activity, remember, activity is the number of decays per second, so it's equal to the negative of the rate of change in the number of nuclei, and the negative of the rate of change in the number of nuclei is equal to the decay constant times the number of nuclei. So now we can come up with an expression for the activity. The activity is equal to the decay constant times the number of nuclei that are present, and that can also be written as the decay constant times the initial number of nuclei times e to the minus decay constant times t. Now let's say that we want to relate the decay constant to the half-life. Well, we can do that. Let's write down the equation n equals n0 e to the minus lambda t. If we're talking about after a half-life has passed, well, after a half-life has passed, the number of nuclei remaining is equal to n0 over 2. right? The number of nuclei at the beginning divided by 2. And I'm going to replace t now with the half-life. So now we just have to solve. Okay, we can cancel out n0. So I get 1/2 is equal to e to the minus lambda times the half-life. I can take the natural log of both sides. Okay, do that. The natural log of 1/2 is the negative of the natural log of 2, if you remember your natural log rules. And then we get a negative sign that cancels out. And if I solve for the half-life is equal to the natural log of 2 divided by the decay constant.